Hello friends, I welcome you in lecture number 2 on series solutions of differential equations. In lecture number 1 we have discussed about analytic function, and in this lecture we are going to discuss about ordinary and singular points of differential equations. After that we will see how to decide series solution of differential equations. So far we have not discussed how to obtain series solution of given differential equation. We are discussing the terminology required for this method, series solutions of differential equations. So we just recall the definition of analytic function. A real function fx is said to be analytic at point x0 if we can represent fx by its Taylor series at that point x0, that is nth derivative at x0 divided by n factorial nth power of x minus x0. This is Taylor series of fx, and this Taylor series exists at point x0 and it converges to fx for all values of x inside the interval of convergence of this power series. Now the main functions which we will require in our topic are polynomials and rational functions. So we can remember that polynomials are analytic at any point x0, and rational functions, that is division of polynomials, say px and qx, rational functions are analytic at those points for which this denominator polynomial is non-zero. So we will mainly focus on these two functions because in our chapter we will be concerning about these two special types of functions only. So again I emphasize, remember that polynomial functions are analytic everywhere, and division of two polynomials is rational function, and it is analytic at those points at which denominator is non-zero. So using this analytic function, we are going to discuss about ordinary and singular points of differential equation. Now we will consider only the linear differential equation of second order. Suppose I consider standard form of linear differential equation of order 2, then it is y double dash plus px into y dash plus qx into y equal to 0. Suppose this is differential equation in which px and qx are called coefficients of differential equation, and we are going for homogeneous differential equation only. We will not go for non-homogeneous ordinary differential equation. So our focus is on linear second order ordinary differential equation. Here coefficients can be functions of x also, and we don't know the methods for solving differential equations with variable coefficients. That is the reason we have this another chapter known as series solution. So whenever coefficients are variable or we have a linear differential equation with variable coefficients, we cannot apply the methods which we have discussed so far. Those methods which we have discussed in the chapter of higher order ODE are applicable for linear differential equations with constant coefficients only. For variable coefficients we have to go for this chapter, that is we have to go for series solutions if at least one coefficient is not constant, or if at least one coefficient is a function of x. So we will discuss how to find out series solution in upcoming lectures. Recently we focus on ordinary and singular point. So suppose I want to check whether given point, say x0, is ordinary point of this differential equation or not. Then definition is, if these functions px and qx, if px and qx are both analytic, if px and qx are both analytic at this point x0, then this point x0 is called ordinary point of differential equation 1. The point x0 is called ordinary point of differential equation 1 if px and qx are both analytic at that point x0. So before using this definition, you make sure that you write your differential equation in this form. Suppose I have this differential equation 1 minus x square into y double dash plus 2xy dash plus y equal to 0. Then first I have to make sure that coefficient of y double dash is 1. So first I will write this, I will rewrite this differential equation by dividing it by 1 minus x square. So I have 2x over 1 minus x square into y dash plus 1 divided by 1 minus x square into y equal to 0. Then I will compare it with this standard form, and here you can see we will obtain px equal to 2x over 1 minus x square and qx equal to 1 over 1 minus x square. So let me write here, after comparing with that standard form, this equation we compare with y double dash plus pxy dash plus qxy, and we find that function px is 2x over 1 minus x square and function qx is 1 divided by 1 minus x square. Now if we want to consider analyticity of these two functions, then we can observe that px and qx are rational functions. They are division of polynomials. Here we have two polynomials, 2x and 1 minus x square. Here we have 1 and 1 minus x square. And we know that rational function is not analytic at those points at which denominator is 0. So we have to concentrate on 1 minus x square. First we decide that at which points 1 minus x square is 0, and answer is it is 0 if x equal to 1 and minus 1. So this px is analytic everywhere except these 2 points 1 and minus 1. Similarly qx is also division of two polynomials, so it is also analytic at every point except 1 and minus 1. So every point which is different from 1 and minus 1 is ordinary point of this differential equation, because px and qx are analytic at every point different from 1 and minus 1. So in this way it is easy to decide whether given point is an ordinary point of differential equation or not. You first write down your differential equation in this form, and then you decide at which points px and qx are not analytic, and the points at which px and qx are both analytic is called ordinary point of this differential equation. Now the point which is not ordinary point, here 1 and minus 1 are not ordinary points, so they are known as singular points of given differential equation. So here we can see that this differential equation has two singular points 1 and minus 1, and it has infinite number of ordinary points except 1 and minus 1. So another definition is singular point of a differential equation. If the point x0 is not an ordinary point of differential equation 1, then it is called singular point of differential equation 1. And ordinary point means these two functions px and qx are analytic at those points. Ordinary points are those points at which px and qx are both analytic. Now if our point is singular point, then again there are two classifications. There are two types of singular points. One is called regular singular point, another is irregular singular point. Now how to decide whether point is regular singular point? So first thing is it must be a singular point. After that you have to decide that x minus x0 multiplied with px and x minus x0 square. You decide these two functions, multiply px by x minus x0 and multiply qx by square of x minus x0. If these two are analytic, at x0, then x0 is called regular singular point, otherwise it is called irregular singular point. So here I have written a singular point x0 is called a regular singular point of differential equation 1 if both x minus x0 times px and x minus x0 square times qx are analytic at x0. A singular point which is not regular is called an irregular singular point. So we can decide for these 2 points 1 and minus 1, which we have just obtained. For this differential equation, we have seen that 1 and minus 1 are singular points. So now we can check whether 1 and minus 1 are regular or irregular singular point. So if I want to check for x equal to 1, then my x0 is 1, and I have to decide, first I have to decide x minus x0 into px. x0 is 1, so here I consider x minus 1 into px. px is 2x divided by 1 minus x square, and this 1 minus x square can be written as 1 minus x times 1 plus x. So let me write one more step, 1 minus x into 1 plus x. This I can write as negative of x minus 1. So x minus 1 will cancel out, and I am left with minus 2x over 1 plus x, or x plus 1. And another function I have to decide is square of x minus x0 into qx, that is x minus 1 square into qx. qx is 1 over 1 minus x square. Again we can write 1 over 1 minus x square as 1 minus x into 1 plus x, and this 1 minus x, or I can write this as 1 minus x square. So 1 minus x will be cancelled out, and I am left with 1 minus x over 1 plus x. Now I have to check whether x equal to 1 is regular singular point or not. So I have to decide whether these 2 functions x minus x0 times px and x minus x0 square times qx are analytic at x equal to 1 or not. Now this is rational function. It is division of 2 polynomials, 2x and x plus 1, and we know that this function is not analytic at those points for which denominator is 0. Here denominator is x plus 1, and it becomes 0 at x equal to minus 1. At x equal to 1 there is no problem. If we take x equal to 1, it is 1 plus 1 2. So this function is analytic at x equal to 1. Similarly here also we have 1 plus x in the denominator, so this is also analytic at x equal to 1. Therefore we have seen that x minus x0 times px and x minus x0 square times qx are analytic at x equal to 1. Therefore x equal to 1 is regular singular point of given differential equation. Similarly I have to check at x equal to minus 1. So for that I have to consider this x minus, if I want to check at x equal to minus 1, I have to decide x minus x0 into px. x0 is minus 1, so I have x plus 1, px is 2x over 1 minus x square, and we can see 1 minus x square is 1 minus x into 1 plus x. This x plus 1 will cancel out, and we are left with 1 minus x. Here this we can write as 1 minus x into 1 plus x, and 1 plus x will cancel out. Similarly we can decide square of x minus x0 into qx. So here I have to write x plus 1 square. Here I have 1 over 1 minus x square. Here also 1 plus x will cancel out, and we are left with 1 over 1 minus x. And these two are rational functions. Denominator is 1 minus x. It becomes 0 if x equal to 1. And we are checking at x equal to minus 1. So obviously these two functions are analytic at x equal to minus 1. Therefore x equal to minus 1 is also regular singular point. So in this way we can decide whether given point is ordinary or singular, and if it is singular then we can check whether it is regular singular or irregular singular. So for regular singular you must make sure that these two functions x minus x0 times px and x minus x0 square times qx are analytic at x0, both analytic, and if at least one is not analytic at x0 then x0 becomes irregular singular point. We can discuss this question about ordinary and singular points which was asked in GTU Winter 2021 exam for 4 marks. So here given differential equation is 2x square y double dash plus 6y dash plus x plus 3y equal to 0, and first we have to write in standard form, so we must make this coefficient 1. So for that we divide given equation by coefficient of y double dash which is 2x square. So we have 6x divided by 2x square times y dash plus x plus 3 divided by 2x square times y equal to 0, and here 6x divided by 2x square, that we can rewrite by cancelling common factors. We can cancel out this 2 and x will cancel out here. So this I can write as, here 2 will cancel out, here x will cancel out, and I am left with 3 divided by x into y dash plus x plus 3 divided by 2x square into y equal to 0. And if I compare with standard form, then I have to write coefficient of y dash as px which is 3 by x, and I can write coefficient of y as qx which is x plus 3 divided by 2x square. Now it is clear that px and qx are rational functions, that is division of polynomials, and the only point at which denominator becomes 0 for both the functions is x equal to 0. So at x equal to 0 px is not analytic, at x equal to 0 qx is not analytic. In other words, px and qx are both analytic at every non-zero point x. So we can write that clearly px and qx are both analytic at every point x which is different from 0. This means every non-zero point is ordinary point of given differential equation. Every non-zero point is an ordinary point of given ordinary differential equation, and x equal to 0 is not an ordinary point. So x equal to 0 is singular point, and if we wish we have already given number 1, so we can write that x equal to 0 is singular point of equation 1. So we have decided ordinary points, and we find that every non-zero point is ordinary point. There is only one singular point, so find ordinary and singular points of the differential equation. So x equal to 0 is singular point of equation 1. Now we can decide whether x equal to 0 is regular singular or not. So for that we have to find out these two functions. We will decide x minus x0 is 0 into px, that is x into value of px is 3 by x. So x will cancel out, we will obtain 3. Similarly, we can find out square of x minus x0 into qx, that is x square. Value of qx is x plus 3 divided by 2x square. So we can see that x plus 3 divided by 2x square will cancel out, and we are left with x plus 3 divided by 2. And it is clear that this is constant polynomial, analytic everywhere. This is also analytic everywhere because denominator is non-zero. So it is obvious that x minus 0 into qpx and x minus 0 square into qx, we are checking at 0. So are analytic at x equal to 0. Both are analytic at x equal to 0, and therefore we conclude that x equal to 0 is a regular singular point of differential equation 1, or regular singular point of equation 1. So it is easy to check whether given differential equation has ordinary and singular points, whether singular points are regular or irregular, and generally they ask this type of question for 4 marks in university exam. So you remember these definitions about ordinary and singular points, and you can easily score minimum 4 marks for this type of questions. Make sure that your differential equation first can be written in this form. Our definitions are for this form of differential equation. So if your differential equation has coefficient of y double dash different from 1, then first you write your differential equation in standard form and then decide px and qx. Otherwise you will get wrong answers. So I have first divided this equation by 2x square, which is coefficient of y double dash, and then I compare this equation with this standard form and I find that px and qx. And after that you have to use definitions of ordinary and singular point. So this is all about this session. I hope you like it, and in upcoming lectures we will see how to decide series solutions of given differential equation. Thanks for watching.